The first type of lipid that we're going to look at are fatty acids. These are the building blocks of the lipids that tend to be used more expressly in biochemistry. And they're really notable by having a long hydrocarbon chain. So here's a great example. The chain is about 16 carbons long if we include the carbon that's in the carboxyl group, which identifies the other side of the fatty acid. And when we have this fatty acid, we have two ends. And this is a really good way to start to look at biochemicals. That we have one end that's hydrophobic, nonpolar, mostly carbon and hydrogen. This is a water-fearing portion. That's the long bulk of this molecule to the left. But then at the right side, we have this polar area where it's a carboxylic acid. We have polar bonds, and this is a hydrophilic portion, a water-loving portion of this palmitic acid. When this goes into reactions, it'll be this polar end that tends to react, and the two ends will be directed by watery environments very differently. This is what leads to a lot of lipid chemistry and function. And so to begin with, though, let's work on identifying these fatty acids. So naturally occurring fatty acids, even number of carbons. What's even more important to keep in mind, though, is this distinction between saturated and unsaturated fatty acids. Saturated fatty acids mean saturated hydrocarbons, and we talked about alkanes, alkenes, and alkynes previously, where alkanes have all single bonds, and when they have single bonds, we fit more hydrogens around those carbons. This is what we mean by saturated fatty acid, that the carbon chain is filled with hydrogens, meaning no room for double bonds. In contrast, unsaturated fatty acids have at least one double bond in their hydrocarbon chains. We can't have all double bonds, so it's not good to think of unsaturated as double bonds instead of single bonds. If we have at least one double bond, that means that it's not filled with hydrogen, and therefore it is an unsaturated fatty acid. And this ends up determining various physical properties of the fatty acid chain as well. As the number of double bonds increases, the melting point decreases. We'll see how this leads to identification of saturated and unsaturated dietary fats very soon here as well. And so for some examples, right, stearic acid here, we have an example of it. This is a saturated fatty acid, and it has a melting point of 71 degrees Celsius. With our general ambient temperature around 20 degrees Celsius, this means that stearic acid is not going to melt until we are above that melting point. So it's going to be solid at room temperature. In contrast, oleic acid has a melting point of 16 degrees Celsius. So if we put it in the fridge, it'll probably solidify, but at 16 degrees on the counter, it would end up already being a liquid because we're above the melting point. And furthermore, if we investigate this double bond more closely, remember that double bonds do not rotate, right? When we have a double bond, it really locks those carbons in place so that they can't freely rotate and kind of bend around in the same way. And when this happens, it means that the configuration of this fatty acid chain is also somewhat locked in place because that link isn't free to rotate. And so here, what's shown is what we call a cis double bond, where the two ends of the hydrocarbon chain that are on either side are on the same side of that double bond. And so they kind of make this V shape. We have an example of this below with sort of a shorter version, this CH3. Imagine this could be a longer hydrocarbon chain. Cis is to say that they're on the same side of the double bond, and trans means that they're going on opposite sides of the double bond. Still within the chain, they're not attached to the same carbon, but cis means that they are going to make this V-like shape in a longer chain where they're on the same side, and trans means that they're going to go opposite one another. If you've heard of trans fats, this is the origin of what makes up a trans fat. And so here that is, right? So saturated fats, trans fats, and unsaturated fats. These are things that we may have heard of before. And so saturated fatty acids, these are free to move around. There's only one type of saturated fatty acid as far as cis-trans. It really doesn't apply because there's no double bonds, and therefore all the bonds between carbons are able to rotate freely. Unsaturated but trans means that the hydrogens are opposite one another, which means that the carbon chains are opposite one another. So same way of thinking about things, and we end up sort of keeping that saturated fatty acid arrangement in some ways. But unsaturated cis fatty acid means that the hydrogens are on the same side, which gives this fatty acid chain a bent configuration. And so when we're identifying fatty acids by where their bulk is and their properties based on this bulkiness, having a cis versus a trans double bond makes very different chemistry. When we're looking at cis versus trans unsaturated fats, right, these are all unsaturated fats that are in, foods or something like that. Most naturally occurring unsaturated fatty acids are going to be the cis variety, and we often think of these as like good fats: olive oil, fish oil, nuts. And a lot of times they're identified by being liquid at room temperature. Remember that these cis unsaturated fatty acids often have lower melting points, which means liquid at room temperature. In contrast, trans fats, and a lot of things that we know and identify as trans fats, like margarine or processed foods, things like that, shortening, these end up being solid at room temperature. They're a lot more like saturated fats in practice than cis, naturally occurring unsaturated fats. And so furthermore, right, you may have heard of omega-3 and omega-6 fatty acids. This also matters, right? I think that omega-3 versus omega-6, we hear about this somewhat in, food and nutrition and whatnot. What does it identify? Well, it identifies where that first double bond occurs as we're looking at our fatty acid from the hydrophobic side working in. Omega-6 has the first carbon double bond at the sixth carbon, where omega-3 has the first one at the third carbon. Again, this isn't like you need to be able to identify everything 100% perfectly, but just know that when we're talking about lipids, where these double bonds occur, how many carbons there are, all this matters because we're dealing with a pretty defined structure. Carboxylic acid on one side, lots of hydrocarbon on the other. Even though it's a straightforward structure, there are a lot of ways that they can be subtly different that lead to big differences in function.